So we will talk about abundance of field galaxies. That's about observational measurements of a velocity function, abundance of galaxies with given so-called velocity. So this is our goal, and this is, I would like to stress, as that's observational. I'm using a catalog from Karachintsev and their expertise on doing all this stuff. And the goal is to construct velocity function. Okay? So in local volume, that's a distance less than 10 megaparsec away from us. There's about 600 Wolf galaxies. Most of them are not satellites. Early type and late types mixed as they should be. And the sample is about 80% will be H1 measurements, but they've also supplement that with the velocity dispersion estimates. So the problem actually is not new, but it came to different kind of a stage or complexity or certainty that actually we start to see quite a bit of a difference here, or difficulty. So this is the early incarnation of the same. The samples which are used before were defined by H1 observations. So H1 selected galaxies. What you measure in H1 is a line width. It's W50 at the half, the maximum. You measure the width. So that will be the measurement of the maximum velocity multiplied by 2 of rotation velocity of the galaxy. You don't track rotation curve. You don't reconstruct rotation curve. You just measure the whole thing. Normally for those galaxies, the whole galaxy will go into one beam and you measure the line width. So now the previous results, it will be high pass, will be this one, will be curve like that. And that's prediction of lambda CDM in our paper with Sebastian Trujillo-Gomez. It will be this one. You start to see some kind of interesting kind of features here. Lambda CDM at the small scales will go as a power -3 in the normal kind of units. It's abundance. And that will be the Sokal velocity. Okay? So one goes in this way, and the prediction are very, very reliable, so to speak. That's a simply measure Vmax of each halo. Okay? And observation will go flat like that. So somewhere at 40 kilometers per second, there's quite a bit of disagreement. But selection here was by H1, and it was the first kind of generation of the whole thing. Later on, we'll see that actually the current observations, observational measurement somewhere around here, but we still have a problem. It's another paper which came later. That's alpha, Manolis Papastergis. And you see the same kind of thing. The results actually start to get more kind of increasing here. You see it's going up slightly. Okay, and this is our previous kind of estimates, which will be here. Now that what's plotted here is a line width. Normally we made a progress. We divided by now by 2, so it will be more comparable with the rotation velocity. But it has the same kind of issue. And what is the problem? At what scale we start to have the deviation, and what will be difference when we start to get to those scales, which will be here. Okay. So now the Karachintsev sample. Let's see again. This is about 600 satellites. When you go to that statistics, you can start to get kind of a feeling that it represents some kind of average universe. It doesn't have big halos by definition, but on average, abundance of galaxies by magnitude, which will be here, that's normally velocity luminosity function, is comparable with the whole universe, so to speak. So this is an example. This is from Karachintsev sample. This is the data done by different cuts in the distance. This will be 6 megaparsec. This will be 8 megaparsec, and this will be 10 megaparsec volume. And this will be those data points with the Poissonian error bars. And we plot here luminosity function from Sloan that end up somewhere around -16, -15, and the 2DF. No twinkling with the normalization. It's just as it comes from the data. There's a bit of offset here which we need to normalize to bring to the same magnitudes, but otherwise this way they stand. So the sample does reproduce luminosity function of universe reasonably well. And this kind of gives us way to estimate velocity function after that. The top one is another beast. That's a fraction of early types divided by total types at the total number of galaxies at a given magnitude. If you look at it here, So now we're going to bright galaxies. About 10% galaxies are early types, as you naively would expect for bigger sample. You go to smaller galaxies, which will be here. The fraction declines. We have something like 5 or 6 or 7%. They are there in the sample. If you come back to, we come on the z side of a luminosity function, the curve starts to climb up. That's mostly will be satellites and dwarf spheroidals. That's why they're going up. It would be here. So now we're looking at a luminosity function. Clearly, there's the incompleteness effect, which will be here, starting up to -14, which is when it comes to velocity function. Velocity, that will be about 25 kilometers per second. The sample is basically complete, and now we make it some correction to those that kind of decline. But correction actually is small. Okay, now this is a different diagram. This we plot the distance. This will be velocity along observed W50 divided by 2. This is what plotted here. The color is a different magnitude, which is here. It's the bright galaxies, which will be intermediate, and this will be the dwarfs. And open triangle, open symbols will be early types, and the closed symbols will be late type galaxies. If you go to small galaxies, you start to see those. The objects which is here, those actually are satellites. There's some bright elliptical galaxies which will be here. Okay. Otherwise, nothing terribly kind of interesting. It covers the space as it should be. The volume increases. This is why we have more galaxies in that part of the diagram than in that diagram. What is that? Few examples of the galaxies. This is not what is used, but it's actually interesting to know how those galaxies actually, what are those. So there's a few examples. That's a Holmberg 1. This is how it looks in optics. This will be in H alpha, and you see clearly a rotation pattern, which is here. And this is that's the second moment of H1 map, of H alpha map. The same is for another dwarf, UGC 8508. This is H alpha continuum, H alpha image. This is how it looks like. That's rotation pattern, and this is the second moment, that's RMS velocities. Okay. Come on. Yeah, this is the same galaxy. Now we could plot actually for that galaxy because we have H1 data, H alpha data, this normal rotation curve, which is here, which is plotted here. That's a deviation from tilted ring model, and that's the velocity of that galaxy. You can estimate maximum velocity will be about 35 kilometers per second. In order to avoid problems with overabundance of dwarf galaxies, we should place it here, and it's very, very difficult to make it. Okay? But again, this is not the data which is used for observations for the velocity function, because as a velocity function, you measure the whole line width, not splitting that signal into bits, which you need in order to produce rotation curve. It's another example, which is in smaller one, Camilo Pardalis B and Begum 2003. That's how that galaxy looks like. This is H1, which extends the pattern of rotation, and that's a measurement of rotation velocity of that galaxy. It's pretty damn small if you think about it. But this is still big because there are some galaxies which clearly there, which is tiny, puny ones called pygmy galaxies. This kind of, we don't know how they rotate, what they're doing. This is image in H alpha. You clearly see some kind of lumps. This is two H2 regions, which is there. There's a bit of rotation here, but it's of course impossible to measure anything. But the galaxy sits there and produces stuff. It shouldn't exist, but it's there. Okay. So now, different information about the sample, completeness now by.
Say it shouldn't exist. You see dwarf spheroidals with incredibly small velocity distribution.
Oh no, those are stripped and everything else. This is just pristine galaxy which sits there 10 kilometers per second, less than 10 kilometers per second.
Sure, but the dwarf spheroidals have to form somehow.
Okay, fine. But it's on theoretical grounds. It's so small that reionization should have killed it, but it didn't.
Right, that just means that we don't understand reionization.
Fine. I agree with that. Go, move on. So, okay, now, yeah. So now, that's another statistics, which is the surface brightness. where the sample is complete in the sense of sort of brightness, with some incompletenesses, because the sample is not defined, is not selected by some criteria, so to speak. It's picking up galaxies in the universe, all of them observed and placing in the diagram. This will be surface brightness is a function of absolute magnitude. And you clearly see that galaxies, when you go to very small galaxies, have very low surface brightness. And it seems to be there's no cut or no apparent cut or problems with the surface brightness. The whole same population is simply going down, down, down in that direction if you go from bright galaxies to less bright galaxies. Another diagram which is here is the extent of H1. Once we measure line width, we need to know at least have a feeling how far that kind of a measurement goes in the sense of a radius. It doesn't exist for all galaxies, but for about 24 of those H1 measurements were done more extensively, so to speak. And now we look at the literature for those different samples. We plot here rotation velocity, corrected for inclination in this case. And that's the last point in H diagram, how far that that hydrogen extends. And on top of that, I plot Navarro-Fink and White with average concentration with different mass. So now those points here, so if you point here, you could draw a Navarro-Fink and White through that point, it will be here. It's close to the maximum. If it's here, you need to correct for some effect that the gas did not fill the whole dark matter halo. But for most of them, the correction which is plotted here is actually quite small. We're talking about 10, 20, 50% correction. So gas does extend to large distance. Distance is about comparable with a couple of RS in the language of Navarro-Fink and White, or close to the maximum. So now let's simply measure that. The first statistics is not corrected for inclination. So you simply measure W50, divide by 2, and count the objects. This is it, nothing else. Okay. The reason why we don't correct for inclination, because correction inclination for those galaxies actually is a pretty kind of shaky because they're small. Okay. So in that field, when we talk with alpha people, we do the same. The main statistic is not corrected for inclination. So all correction inclination goes now to theoretical predictions. You make a prediction of distribution of true line widths, and afterwards you assume random orientation, and you get statistics observed. So this now is a simple observations. At least it's on a local volume. You see those data points which go in here. Error bars are Poissonian error bars. Again, it's actually a pretty good sample because there's 600 objects. You can slice in 10 bins. It still gives you pretty large number of objects. There's a systematic excess of brighter galaxies on the most brighter galaxies, a factor of 1.5, just what it is. But we go to smaller objects, statistics quite reasonable. So now we plot. I plot now high pass, which will be this curve, and alpha. That's approximation from the previous results. And results are pretty much consistent. Local volume goes systematically above high pass and alpha. And there's a good reason because in those magnitudes we have early type galaxies which are included. So that curve now represents, that kind of curve, represents velocity function of the whole universe, so to speak. Here, statistics is good from large samples, and we add the contribution for early types. It doesn't go to larger distances, larger magnitudes, which will be here. So, and this is what kind of where we stand. Finally, we start to get some agreement between different groups and doing all this stuff. That's another way. It's not yet published results. This is from Papastergis. Again, distribution of the same half-light widths, which will be here, and abundance, which will be here. So local volume is the red points, which go in this way. The blue is alpha 2014, and high pass is those data points. You see, they're quite noisy here because they start to run up their statistics and their sensitivity, but overall there is a pretty damn good agreement between different groups. So now let's start to compare that with theoretical predictions. So theoretical predictions come in here with those lines. The velocity function is measured from simulations. That's a Bolshoi and Bolshoi-Planck simulations. And afterwards, we extrapolate that to smaller velocities. Because at those scales, the velocity function, which is here is a dashed curve here. That's for Planck cosmology. It's a pure power law with a slope about -3. It's still under debate with the 2.9 or -3, but it's basically done. This is what it is. From here, from the dashed curve to red curve, that's a correction for baryons. Simply abundance, how much mass in baryons will be in the central part of galaxies. You move that slightly in that direction. So this is a correction for baryons. It will be in that direction. And from here to here, that's a WMAP 5, and this is a Planck. Planck slightly predicts slightly more abundance here. So now we compare with local volume data, and again, this will be the same for or very close to alpha and theoretical predictions. And there's one kind of a pleasant part. So in that part of diagram, we seems to be reproduce abundance of observed galaxies, which is good news. Now, when it deviates, it's not clear exactly what it will. It will be maybe 60 kilometers per second, which is the Magellanic Clouds, or maybe 80 kilometers per second. But somewhere around here, we're doing pretty reasonably good. Okay? And afterwards, one goes up, all the way up, and the one goes to -1. And of course, once we get to something around here, we start to see that kind of normal problem. Okay. Warm-dark matter. So results are taken from Schneider et al. 2013. They gave me the approximations, the tables, which are approximated with different for different neutrinos. So those neutrinos are thermal neutrinos. And you see that velocity function of a thermal neutrinos behaves this way. So that the feature here, that's a mass of neutrino. Neutrino dumps fluctuation on very small scales, and this is why it starts to decline here. On the large scales, neutrino doesn't do much for our spectrum, and we approach now normal random CDM kind of approximation, which will be here. But that feature is a generic feature for warm-dark matter. Wipes out fluctuations too much on the small scales, will be always this feature. You can probably massage neutrino kind of a model to avoid that, but this is what standard kind of neutrino model predicts. And now let's start to compare with observations. The first step is effect of a projection. So this will be lambda CDM in the 3D velocity function, full velocity function, and this will be W50 divided by 2. That goes down because of the projection, and the same will be with observations. It's the same kind of a feature. It's not bigger effect, but it should be corrected once we start to do comparing with observations. This is the summary. The lambda CDM, Planck, WMAP 5, which will be here again, will be this one. Observations plus minus 15% goes at red strip will here, and warm-dark matter is doing that stuff, and keep going, depending what kind of mass you're doing. And that mass is already small. That's not compatible with the clustering of Lyman alpha clouds, but it's how it behaves. So you can reduce the problem here, but will be excessive. The problem will be on a smaller scales. So warm-dark matter seems to be doesn't reproduce the shape kind of observed function. And it's clear why, because this one has a mass scale included, and this one doesn't have any kind of indication of a turnover. Okay. And this now is in a three-dimensional space. It's normal velocity function. So now let's compare that with a field Wolf problem with a local group problem. So now local group problems, this is the result from Kravtsov 2010. Normal kind of a band of satellites in the local group. This will be here. The number of galaxies is more than given circular velocity, and this will be the theoretical prediction. Again, it's going -3. It should be going this way, depending on what mass you're taking. For primary, it could be higher or could be low. So now actually reasonable estimate is 160 kilometers per second for dark matter will be that curve. If you increase the mass, it will be that curve. No surprises here. So now if you do too big to fail problem is around here. So you take that point which will be here. If you compare it with that point or that point, you over predict the abundance of relatively big satellites. But now let's have a look at 30 kilometers per second and above. So I could make it work reasonably well somewhere around here with the 10 to the 12 solar mass halo, which will be here. Now, if you go to, and will be the same for
how much?
What?
Is it 10 to the 12 solar mass?
For primary.
Oh.
For our Milky Way, that's 10 to the 12 solar mass. It's 2 10 to the 12 or 1, something like that. Yeah. It depends. So now at the same velocity cut, at 30 kilometers per second and above. So we take that line here, which is that kind of ellipse. Okay. So this is what is observed at 0.6. This is what measured. This is what predicted 5. We have the same problem, but it's much worse. Okay. The first, those are not satellites. Most of them are individual galaxies. They sit in the peripheral part of other big ones or in between. Those are also not satellites. And the problem is significantly bigger numerically, but this is what kind of where it stands. Now, hydrodynamics is still kind of at the beginning, so to speak, but we start to get some results. This is from Kansas talk. The slope, once we start to put all this hydrodynamical effects, that's Vela simulations by Daniel. It's one of those we took, and this is the abundance. It's a function of real mass and everything else. This is what she presented. And this is a velocity function of those observed satellites. Those are preferentially in a larger distance away from the central part. It keeps going up with a slope about -3 like in a dark matter. And that's what it should be. If you'd like to reconcile satellites, we observe the satellites in the Milky Way reconcile those. Okay. We clearly see some kind of a problem here. And if you look at results of simulations, now it seems to be everybody start to get some kind of agreement that for those small galaxies, the Klypin code clearly exists, but depends how you massage the data. But at the same time, the issue for velocity function is on a different scale. And this is an example. This is the most extreme example. This is of Madaushan and Governato 2014. Was that Bashful and Dock, and whatever it is from seven dwarfs. There is a core in those simulations, but the core is actually relatively small. In order to, and this is a diagram, to what distance we actually measuring those velocities in H1. Those velocities measured is about 3, depending on what we stand. This is those 2 will be around here. Those will be measured at 3, 4, 5 kiloparsec. So the core is here. We go to 3, 4, 5 kiloparsec. The mass is actually there. It didn't change much. The simple reason for that, because when we start to trash the central part with all these explosions, dark matter particles migrate out, but they don't actually thrown out. They simply move from the central part to those 1 kiloparsec or 2 kiloparsec. So the result with mass within 3 kiloparsec did not change much.
Which simulation are they using?
Which simulation?
What are, well, obviously.
7 dwarfs. It's called 7 dwarf simulations. So those 2, Bashful and Dock, it's at 22 kilometers per second, 43 kilometers per second. Those are kind of those are satellites which will be about here. Okay. So not obviously the cores or formation of a cores in those dwarf galaxies actually help. You might do it even more. In this case, a mass within 3 and 5 kiloparsec also will go down, but it's very, very difficult to do it. In order to solve the field abundance problem with the stellar feedback, whatever kind or you would like to do, 30 kilometers per second galaxy should reduce a mass 5 times within 3 kiloparsec. So whole galaxy, it's not like a central part in the core. The whole galaxy should be puffed up, dark matter galaxy. So which could be possible, but I don't know how actually to do that. Okay. Too big to be, I have 2 minutes, right?
Yes.
Yeah. Too big to fail. It's originally was a problem with a structural problem with the satellites. It's too dense for satellites in the range of 20 to 30 kilometers per second. We think in this kind of, in this room, we have Eddie, and we have Kenza, and we think that that problem can be solved by combination of RAM pressure stripping and a tidal stripping. So it's different problem because it's a problem for satellites. But later, or recently, James Bullock migrated to a different problem on a different scale, which actually is a similar or kind of hiccup of a problem which we see with the field galaxy, but much clearly, so to speak. So now let's. No, doesn't want to go. And That's an interesting kind of a statement. There is no too big to fail problem. The problem is nobody fails. Too big to fail meaning somebody fails, but those don't. The problem with the simulations, if you look at all simulations we've done so far, and our simulations with Daniel and Chris Brook simulations and Phil Hopkins simulations, none of those galaxies actually are failing. So too big to fail implies somebody failing, but no. The problem is that there is no failed galaxy. Okay? Reionization doesn't kill the galaxies, and the Kenz represented the curve, how star formation happens. So the galaxy go to the very small galaxy, which goes through reionization. Well, it declines, star formation declines quite a bit, but the galaxy is still in place. Okay? Supernova feedback doesn't kill galaxies either. So none of those recent simulations kill any of those galaxies. 10 kilometers per second and up. So let me summarize what we'll hear. What cannot help? Okay? To solve that overabundance problem, which is here. The supernova 2 feedback, there's not enough supernovas. It seems to be. Okay? It's impossible, that will not be solution if we turn dwarf irregular galaxies to dwarf spheroidal galaxies. Dwarf spheroidal galaxies in the field don't exist. Everybody, in all these samples, we do have dwarf spheroidal galaxies, but those are actually satellites. In the field, they don't exist. So turning them and not seeing them in luminous part is not an option. Okay? No star formation at all doesn't help at all, because in this case we will see H1 clouds with quite substantial mass. Those should be observed. Those should be observed and don't exist again. When all these H1 surveys were done and look at that, do we have luminosity associated with those H1 clumps? No, there's not such things. Those exist. They all have some luminosity. Okay? What could possibly help is a large population of very low surface brightness, much low surface brightness, what we see. You push the gas out, but you hide star formation or the stars below kind of observable limit. Very efficient stellar feedback. That's another possible explanation. You shoot two supernovas. The gas is gone. You don't see any luminosity or lack of self-shielding in small dwarfs. You start to speculate, but it's actually difficult to do it.
Thank you, Anatoly.
So Anatoly, something I've always wondered about with regard to the H1 luminosity functions from HiPACC, alpha, etc.
I know, but the luminosity function.
Well, the H1 mass function.
Mass function, okay.
Yeah, the H1 mass function.
Yeah.
21 centimeter.
Okay.
So you made a big point of distinguishing between the field and sort of clusters or groups, and the problem is the samples that we have from alfalfa and HiPACC are very much limited to the Milky Way's immediate neighborhood.
No, not at all. In alpha is a distance, I don't remember, 50 megaparsec or something like that. It's not local.
Is that big enough that we can be confident that
10 megaparsec.
an unbiased sample of the cosmic volume?
10 megaparsec is good enough. That's the point. Even 10 megaparsec. For some, because you have statistics, you have hundreds of dwarfs sitting there, and you just saw the quality of luminosity.
Are you confident that environmental effects, for example, ram pressure stripping on H1, aren't different 200 megaparsecs from the Milky Way compared to what they are 20 megaparsecs from the Milky Way? That's my work.
In that, most of the galaxies will be there, and they suffer from that effect as much they could do. Remember, the fraction of volume in big clusters of galaxies actually is quite small. So when you do count the small galaxies, this is what you will see. And this is why was interesting to see that velocity function, not mass function, but velocity function of a bigger samples and velocity function in the local volume actually are very, very close.
Sandy, last question.
So, as I've looked at the data, I've been struck by the fact that you could make sense of the number counts and certain other aspects of these galaxies. You just decided that for some reason the velocity is bigger than they're too small. And I don't know if this thought has occurred to other people, it probably has.
It's always.
Hold it. And I was really struck by the talk by John Cornby at another conference which he took a different cut in his usual way of doing scaling calculations, et cetera, et cetera. And he had a different population of field galaxies and showed that he could get good continuity between this new population and the traditional dwarf spheroidal population if he assumed that velocities were wrong by a factor of 3 or 4. Exactly the same effect that would fix most of these observations.
I don't know how he scales, so what kind of calculation he takes. Now, observation is that's a very, very difficult to do because those 20 meters per second complete sample is only within that kind of dimension. If you do it by open. Right? It always was a clear solution for all overwhelming problems. You multiply the velocity, observed velocity by 3 times, and
No problem.
No problem. This is the whole thing. Yes. Once you go from that kind of, and you don't play any games in the observed, you don't think.
Thanks, Anatoly. Then, and